Hello! So, in this video we're going to do the theorem that says that if the series AN converges absolutely, then it converges. So if you recall, we talked about this in terms of integrals. We talked about if something, the absolute value, if the integral of the absolute value converges and, is well-defined, Riemann integrable, etc., that doesn't actually on its own mean that the regular one is Riemann integrable. You have to do you need a little bit of extra hypothesis. So in this case, that is not the case. So in this case, you actually do get that an absolute convergent series gives you that the regular series converges. I also take a moment to point out that this is where the nuance of the terminology for convergence is important, because I've written the same thing twice, right? So when I say converges absolutely, what I mean is this thing, the absolute value of the ANs, the sum of that converges, implies that just this thing converges, right? All right, so this uses a really kind of a cute little loop to get around a lot of the annoying notation and such. So let's do the proof here. So I'm going to define Bn to be AN plus the absolute value of AN. Now this seems like it's a weird choice, but bear with me. So first of all, it's worth looking at this and seeing what's happening here. So if AN is, so note or notice, then on the one hand, if AN is a negative number, like -7, right? I'm going to have -7 plus the absolute value of -7. -7 plus 7 is 0. So if AN is a negative thing, Bn is going to be 0. So in particular, 0 is the smallest that Bn can get. On the other hand, if AN is a positive number, like +5, then the absolute value is the same thing. I'm going to get 5 plus 5 is 10. So the biggest it can be is 2 times. I don't want to write AN in case AN is negative, right? So it's 2 times the absolute value of AN. Right? Where AN is positive, that's where I get this instead of 0. But if I just wrote AN there, then I'd be claiming Bn is between 0 and 2 times AN, where 2 times AN might be -14, and that doesn't work. So the important thing here is that Bn is a non-negative value. By hypothesis, we have that the series AN converges. Say to S. But that means that plus a series Bn, well, Bn is less than or equal to 2 times this thing, right? So it's less than or equal to the series 2 times AN, which is really just 2 times the series AN, which, because it's an absolute, right, this is absolute value, so this is a increasing up to S. So this is less than or equal to 2 times S. Right? Where, again, I'm being a little, maybe notationally sloppy, so I should probably put something like n equals 0 to infinity on all these things. I wasn't, because, again, we're talking about convergence, so where it actually starts isn't the important bit, right? But nonetheless, we should be sort of nice and consistent. So this Bn then is bounded above, but Bn, as we mentioned, was non-negative, so it's an increasing series. So the series Bn, and going 0 to infinity, converges. Now if I take 2 convergent, and in fact absolutely convergent series, I can put them together, meaning that this converged, so the series absolute value an, or in fact, let me actually do it this way. Sorry, let me erase this. I could have gone with that, but it pedagogically better to do it this way. Except I forgot my words. Use your words. Sorry. I also need a new cloth, it looks like. All right. So, therefore, the series, so I have that Bn converges, I have the absolute value of An, that series converges. So in particular, I can take Bn minus the absolute value of An. Converges. But, right, because they separately converge, so I can put them together. But Bn minus the absolute value of An, if I remember how I defined Bn, this is just, in fact, equal to An. And so I've actually shown that An converges. That's it. Okay. So this is a nice, cute trick, a nice way of making sure that you get something that is non-negative, and then you can use some sort of overestimate in order to get that it's bounded above and all of that stuff. All right. That's it.